Okay, just a sound and video check. I believe you can see the slides. You should be able to see the title slide for Thursday of week 10. Just doing an audio check. Thank you very much. That's great. I'll go offline for a few minutes and we'll commence the lecture at 4:05. See you then. Okay, good afternoon. We're just going to kick the lecture off now. I'll keep an eye on the questions lectures channel, and you can let me know if there's any problems with the audio or the video. Brenton's monitoring chat, and I think I can see Sarah there too. So welcome to this afternoon's lecture. The topic of the lecture today, one topic, and that is the assignment 2, which was released on Blackboard on Monday. And so what I'd like to do for you today is give you a high-level view of what the assignment's about. I can see in the in Discord that there's been quite a lot of discussion already about some of the details of the assignment. There's also been some questions about how it's assessed. Other students may not yet have had a chance to look at the assignment. I'm hoping that most have, because we wrote the week 10 lab sheet that students have been working on in the labs this week, specifically around getting students up to the point at which you can get your teeth into the assignment. So the topics today that we're going to cover are all about giving you the information that you need to complete the assignment. That means a little bit of a high-level revision of content that you've seen earlier in the semester, and then presenting some of the key details which are in the assignment sheet, but that I think might be helpful for you to hear from me in a video presentation this afternoon. So you can see the topics there. We'll work through all of them, everything from key assignment information on dates and such, right through to some strategies that I'm going to suggest for you to go about the assignment. So the assignment was released on Monday of this week, and the due date is Monday the 31st of May. So if you think like I do in terms of calendar weeks in semesters, that's the Monday of week 13. So it's the week prior to the exam week. So the university rules are that we don't present any material in week 13 that's new and accessible, but we are able to assess students in week 13, and work that you do on the assignment certainly puts you in good stead for the final exam to come in on the Tuesday of week 14. I'll say more about the assignment next week, and then we'll have some more details to follow. But I don't want to talk about the exam rather. I don't want to talk about the exam today. I want to focus on the assignment, but I can see a bit of discussion starting up in Discord around the exam, and I'll have more to say about that next week. Okay, so the assignment's worth 15% of your course grade, and the assignment sheet is located in Blackboard. The assessment folder. We've made a number of revisions to that assignment, fine-tuning it this week, and so that's you always advised to go to Blackboard and check you got the most recent version. The revisions we're anticipating from this point are going to be fairly minor, but they might clarify. We typically monitor the chat in Discord. If there's any uncertainty or ambiguity or typos, we fix them, and the assignment sheet's updated. But the major pieces are absolutely in place now. What you'll ultimately upload is one Python file, and I'll talk more about the structure of that file later today, and you'll upload that as an assignment submission. And so just like for the first assignment, marking of the assignment will take place in the week 13. So the idea is that everyone has the same submission deadline, 9 AM, Monday the 31st of May in week 13. And then through the course of week 13, students get to demonstrate their assignment to the demonstrators. And there's some particularly relevant comments I want to make later about the way that which that demonstration is going to take place. So there was a marking guide released earlier today, and I've got a few more details later in this lecture. So that's some high-level structural stuff about the assignment. I want you to cast your mind back to week 7, where Sarah presented some material on representing colour images as three-dimensional arrays. And before we look at how that data is stored, I want to give you an image that gets you to reflect on why we need to store the information that we do. So if you look at an image such as the one you see on the slide here on slide 4, we've got a small icon that consists of a grid, a rectangular grid, a square grid in this case, of pixels. And if you zoom in, as we can on this icon, if you zoom in, you'll ultimately see that the image is actually constructed of this grid of coloured points. And so each pixel, each box in that image has associated with it a colour. And towards the bottom of the slide that's displayed there, you can see 3 pixels that have been highlighted. One of them's a sort of a greyish colour, one of them's a brownish blackish colour, and the other one's a yellowish colour. None of them are perfect, but they're sort of, well, they're sort of grey, black, yellow. Okay. Now, here's the key point. To represent each colour, be it grey, black, yellow, or any other colour, we need 3 numbers, or at least 3 numbers. And the ones that are the 3 numbers that are identified in the slide that you see on the screen here now are numbers that represent the red, the green, and the blue components of the overall color. So let's choose one here. Let's choose the yellowish color. It's got 90% red, it's got 90% of green, and 0% of black, blue rather. And so we'll talk about what those percentages mean, but they're numerical representations, and there needs to be 3 of them, at least 3. That 3 is the magic number that we work with in this assignment that represents each color. So you can see that there's quite a bit of data storage with that image. We've got the image, which has a number of pixels in it. And for each pixel, we need to store 3 numbers representing the red, the green, and the blue components of the color. So this is a slide I've slightly adapted from one that Sarah presented in week 7, which was, we can think of it, we actually need to use a 3D array. So whereas you think of a 2D array as like a square or rectangular grid, I tend to think of a 3D array in my mind. I tend to think of it as a cube or a prism, where we've got a 2-dimensional array, and where each entry in the array is itself a length 3 array, because we need to store the 3 numbers that represent the color in red, green, blue format. So each entry in this 2-dimensional array that you see on the slide there now is itself a length 3 array, where the numbers where each entry of the larger array maps to 1 pixel in the image. And so, for example, if you want to display a pure red color, you can choose the number 255, and I'll talk about the significance of that number in a moment. It's got red component maximum, green component 0, and blue component 0, whereas green is no red, maximum green, no blue, and so on. And a mixed color like purple has a bit of red, a bit of blue, and no green. 65, 0, 125. So these are numbers that are representing the red, green, and blue components of the image. So one of the things you will be dealing with in the assignment is the manipulation of data in 3-dimensional arrays. Sometimes you'll need to know all the red pixels in an image. Sometimes you'll need to know all the green pixels in an image, and so on. And so you're going to be applying some of the methods that you've been presented earlier in the semester to dealing with 3-dimensional arrays, and you'll be applying them to these image processing tasks that we've set in the assignment. So I've mentioned red, green, and blue as probably the most, in some ways, the most natural way of representing the color of a given pixel. But in terms of processing the images, red, green, and blue is not the most natural color space. So in my mind, I tend to think of these spaces as like three-dimensional spaces like that we live in as humans. There's, and you know, an X, a Y, a Z component. There's a red, green, and blue component. But there's an alternative color space known as HSL, or hue, saturation, and luminance. If those terms are new to you, don't worry, you're not meant to know about them in advance of this assignment. And Brenton's written some really nice explanatory material in the assignment sheet that talk about the interpretation of what hue, saturation, and luminance means. But the key point that I want to discuss with you right now is that red, green, and blue, and hue, saturation, luminance, RGB, and HSL are just two different ways of representing the same color. And one of the key themes in the assignment, and one of the reasons we've chosen the assignment in the way that we have, is that it's possible to move from red, green, blue, or RGB color space to HSL color space, do some processing in the HSL color space, and then come back to red, green, blue. And so there's some really nice applications of representing data sets in 3D arrays, converting those data sets from one format to another, doing some processing in that second color space, and then coming back to the original color space. And those ideas are actually really powerful ideas that pervade all sorts of engineering. Sometimes it's necessary to take the raw data, convert it into a format where you want to do some processing, do the processing, and then once that's done, map back to the original space. It's a really powerful idea. And so the assignment gets you to step through the process of converting RGB coordinates to HSL and backwards. And in fact, if you've had to go at the week 10 lab sheet this week, you'll actually have used external libraries that do that conversion for you. So heads up, one way that you can use to test and debug the code that you write for your assignment is to make use of those external functions to test your code against the library versions of those conversions. The libraries that are permissible in this assignment are spelled out very clearly in the assignment sheet. And when it comes to submitting your code, you need to to use only the libraries that we've identified. But for testing, it's a great idea to test your code against some library code. And the point being that whether you use your code or the library code, you should get the same answers for these RGB to HSL conversions in both directions. And whether you're using RGB or HSL, it's in the intensity values are stored as numbers with a prescribed minimum and maximum values. And the two ranges of numbers that we'll use in this assignment are floating point numbers, or floats, in the range 0 to 1. So fractional numbers, if you like, represented in digital form, and integers in the range 0 to 255. And in fact, we'll be going backwards and forwards between those two, between floats and integers in ways that are spelled out in the assignment question sheet. Something I want to show you here is what's known as a color picker. So this is a link. If I follow that link, what you see here now is a color picker, and that allows me to, you'll see right in the middle here, we've got RGB and HSL. I don't want you to fixate too much about what the interpretation of those numbers is, but just that they are numbers that you can manipulate. If I scroll down here now, scroll down to the bottom, I see a red, blue, green color mixer. And we've got little slider bars here. And if I move the slider bar, if I turn red right down, if I turn green right up, if I let blue be right down, you'll see I get a green color. And if I mix maximum red, no green, maximum blue, I get a purplish color, pinky purple color. And all the while, you'll see the numbers at the bottom of the screen here changing. As I change the green component, you'll see that both the RGB representation of that color changing. And likewise, if I change the red slider bar, color changes, but also the numbers change at the bottom. You just zoom in, make that a little slightly bigger again. Make it slightly bigger. And now I'll change the slider bar and you can see the numbers changing, but also the color changing. So what you see here, there's a link to it in the lecture. That's known as a color picker. And what that allows you to do is, it's one way, it's not the only way, but it allows you to test your conversion between RGB and HSL format. So you can see here, if I go back to the top of the color picker page, you'll see these numbers here that I'm going to highlight in blue, RGB and HSL. If I choose a different color, I get different numbers for RGB and HSL. And so one of the key things in the assignment that you'll be working on is actually doing the calculations. The calculations are completely hidden from you by the color picker. But in this assignment, you'll actually get your hands on to write the equations that move you backwards and forwards between RGB and HSL. Now, I've mentioned on slide 16 here that there are two different ways of representing the intensity values for color image processing. One of them is to use floats in the range 0 to 1, fractional numbers in the range 0 through to 1, or integers in the range 0 to 255. Along the way, the assignment's going to make use of at least 4 different data types that are available to you through the NumPy library. One of them is a representation of integers in the range 0 to 255, so 0, 1, 2, 3, and so on up to 255. And that's got a data type of uint. I don't want to go into the terminology of what uint means. If you're an electrical engineer or a computer systems engineer, you'll learn about that in later courses, and you're welcome to look up details on that data format. I don't want to talk about the details here, other than the uint8 data type is used for representing integers in the range 0 to 255. Occasionally in the assignment, you'll need to use something called the uint16, which is an integer in the range 0 through to this number here, 65,535. Don't worry about the significance of that unless you're doing computer systems engineering, in which case it'll be absolutely pivotal that you understand the significance of that number. So these are the top 2 dot points here represent the integers that we'll be using in this assignment. For more detailed and accurate representation of color intensities, it's necessary to use float numbers, floating point numbers, and there's 2 different precisions associated with those numbers. One of them's float 32, called single precision, but if we want the highest quality numbers that we want to deal with in color processing, we use something called float 64, which is a double precision float. The numbers here, the 8, the 16, the 32, and the 64, they refer to the number of bits that are used to store those numbers. That's a level of detail just outside the scope of this course. The main point, though, is that the double precision float occupies 8 times as much storage as space as a uint8 number. And so what that means is that when dealing with images where we're trying to keep the amount of data storage low, often we use uint8 to represent those images. When we're processing the images, it often makes sense to use float 64, as much precision as we can. So one of the themes of the assignment, again, is to get you to move backwards and forwards between these 2 different types of number representations. So what's the structure of the assignment? Well, it covers the basics of digital image manipulation, and you're going to learn how to use some of the tools behind the scenes when you use if you ever used an app on your phone to process an image, to change the color settings, for example. What you'll be doing is some of these conversions that we're going to look at in detail in this assignment. This assignment just about brings in just about everything into play that we've seen through the course of the semester. Data types, variables, arrays, in this case 3D arrays, so a bit of file processing, both reading and writing files, some iteration, lots of iteration actually, and also some flow control, some if and then else statements. So this assignment really brings together just about everything we've used, not quite everything, but just about everything we've used in the course of the semester. So the way that the assignment's structured is that there are 5 functions that are like a preamble to the assignment. There are no marks for these questions, but the functions that you write in these 5 functions are required for the later questions where the marks are available. So the idea of the first 5 functions is that you can get as much help as you like. I've said unlimited in inverted commas there, meaning that the demonstrators, the teaching team, your fellow students, Discord, any sort of chat that you want to use or assistance you want to use is necessary, is possible, is permitted. There are no marks available for these questions. The caveat is that ultimately you'll submit the code to those functions and it needs to be your own work, but we want all the students in the class to be able to get to the point where they've got those functions available. If you write, once you've written those 5 functions, you are off to a huge start in understanding the ideas that will give you the marks for your assignment. So we've deliberately structured in this way. You might think that's a strange way of structuring the assignment. Why ask you to write 5 functions if they're not going to be assessed? Well, the point is that we want you to be able to feel totally at liberty to seek as much assistance as you want to get your understanding to the point where you write the functions that score your grades. So we've deliberately chosen it that way. The alternative would be to say, well, there's marks for the 5 functions, but we can't help you, or we're able to give you limited assistance. I prefer it we do it this way, where there's functions that you need to write, but you're able to get as much assistance as you need in order to get you up to speed. Because if you understand those 5 functions, to be honest, some of the functions that follow then in the next 8, which is where the marks are, they will be so simple as to almost be trivial. And so there's a bit of work to get your head around the first 5 functions. Having done that, some of the functions that follow where the grades are, almost done in one line, if you know what you're doing. The other aspect of the assignment that we've chosen very deliberately is that the functions where the grades are, which is the 8 functions that follow the first 5, they can be attempted in any order. That's unlike assignment 1, where as you move through the questions, you needed to finish one question or one task before you move to the next. And that was great for that particular assignment with the GPS processing, but we wanted a different structure for this second assignment. The functions, these 8 functions where the grades are, they can be implemented in any order. So you might choose to do them in an order that makes sense to you based on your knowledge. You might run out of time. You might only implement 4 of those functions. You're in line for partial marks, but you won't be held up for completing one function before you need to attempt the next one. So it's been very deliberately structured in a way that once you've got your head around the first 5 functions and you're at the point where you're going to start attempting to write code for the Python functions which get your grades, it's up to you which order you choose them to do them in. And I think that flexibility is really important at this time of semester when you are busy gearing up for a final exam in this course, gearing up for final exams and other assessments in the other courses that you're doing. I think it's really important to give you an opportunity to do as much, or indeed as little, as you want for this assignment. So we've deliberately structured it this way. So here are the 5 getting started functions in blue. These are the functions that you're asked to write, and the assignment question sheet gives you quite a lot of detail about how to do that, what the inputs are for each of the functions, what the outputs are, how to test your code. I'll say more about testing in a few minutes. And so here are the 5 getting started functions. The first 2 are the functions that you'll write to be able to read an image file. So for example, a JPEG file, you'll be able to read that into a 3-dimensional NumPy array and then look at the values of each pixel, which are the color of each pixel. And the save image lets you take a 3-dimensional NumPy array, interpret it as an image and write it out as an image file. So they're useful building block functions, being able to load images and write them back out. The next 2 are these interconversion functions that I mentioned before, moving between red, green, blue, and HSL, or hue, saturation, luminance color spaces. And so in this week's lab, the week 10 lab, if you've got to the question where you're using the external library functions to be able to convert a pixel from one format to the other, you're actually going to write your own version of those functions in the assignment. So for curiosity's sake, it's interesting to see how these transformations occur. And the reason for doing that is that red, green, blue is a very natural way of representing colors using different color display technologies. For example, the representation of colors as red, green, blue maps very easily to display technology using of different types. Processing the images, though, is not necessarily so easy in RGB format. So the idea is to convert them into hue set into HSL, do the processing there, and then convert back. So the 2 functions, RGB to HSL and HSL to RGB, they're the next 2 of the getting started functions that you'll write. And the 5th one is to display an image in the window. So the 5 functions you see there in blue, they're these first 5 functions where you can get unconstrained help, I should probably is a better way of putting it. And if you understand, if you've written those first 5 functions, then by definition, you've got your head around dealing with 3-dimensional arrays, representation of color in RGB and HSL format, and you've got all the building blocks you need to score marks to be awarded marks for the next 8 functions. And here they are in red to distinguish them from the blue font for the first 5 functions. Here are the 8 functions to be graded in the assignment. Here's the first 4 of them. You probably, if you're anything like me, you probably used many of these terms before without maybe wondering too much in detail about how they work. This assignment will fill in those gaps in your knowledge. Things like brightness, contrast, saturation, tone settings for images. They're all processes that are most easily done in the HSL space. So you'll be taking brightness. You'll be able to test your code by taking an RGB image, converting it to HSL space using a function that you've written, adjusting the brightness, and then moving back to RGB for display. So they're the first 4: brightness, contrast, saturation, and tone. And the next 4 functions are cropping, adjusting the size of an image, and plotting some statistics about the image, the colors that are used in it, and some other statistical information around clipping. And then the final function is unsharp mask. Now, which is sort of like used to sharpen up the blurry edges of an image. You'll see there are 8 functions there. Just to cycle backwards between them on pages 10 and 11. The first 7 of them are worth 2 marks each. So your implementation of those functions is 2 marks each. The final function, unsharp mask, is only worth 1 mark. That doesn't mean that unsharp mask is the easiest question. In some ways, it's the hardest question. So if you're looking for a really high mark in this assignment, unsharp mask will probably be the trickiest function to implement. That said, if you really know what you're doing, you can implement a solution to unsharp mask in a single line of code. And for many of these other functions, the implementation of them is, you're not going to be writing hundreds of lines of code. It's actually a handful of lines of Python code to be awarded the marks that you need to. So here's some strategies. I'm conscious I'll lay them out here. You might find coming back and referring to these later as you progress towards a solution might be handy. The first one is guidance to read the manual. And in this case, the manual is the assignment question sheet. There's a ton of useful and relevant background information in the assignment sheet. I can say that when I read the assignment sheet that Brenton drafted, I certainly learned a lot of things, and I think you will too. So it really is lots of useful and relevant background information. You'll find yourself having questions answered that you didn't know you had, and if you get your teeth into the assignment, you think, I wonder why things are done that way, go back and refer to the assignment sheet. It is really helpful. I already mentioned before that it's important to go and check the most recent version of the assignment sheet, but I'll say it again. We strongly recommend that you complete this week's lab sheet before starting the assignment. The week 10 lab sheet was specifically drafted to take you to the point where you can start writing these functions here, the getting started functions. None of the steps in the week 10 lab sheet is particularly difficult, but it takes you in baby steps to the point where you're starting to work with the files, you're starting to understand the three-dimensional arrays, you're starting to understand the color spaces. So it's highly recommended that you complete this week's lab sheet before making a start on the assignment. Strategies. One of the strategies for the assignment is to take small, tiny steps. This is actually one tiny instance of a broader topic that we touched on earlier in the semester, which is around debugging strategies. It's pretty easy to say, here's I've applied my function to an image and I get this other image. Is this right? Is my function, is my code working? I'm stuck. Debugging strategies is something that you will find are necessary to make progress in the assignment. None of the steps is individually is that hard, but when you put enough of them together, you get some complexity. Another strategy is testing your conversion against the color picker, going backwards and forwards between these two different color spaces. I gave you a link to the color picker before. There's also code in pointers to code in this week's lab sheet that allow you to do these conversions. So you're not being asked to write code and then guess if you're right. You can test if you're right. And as an engineer, that's a great point to be, where you're developing a solution and you want to test your solution. You've got test cases that you can call upon, either in use of color pickers or external library functions, to check if your answer's right. So rather than saying, is this right, you'll be able to check if you're right. So you'll end up submitting a single file, and your uploaded file will contain definitions and code for the 5 getting started functions and maybe up to 8 accessible functions. I say up to because you might choose to implement 4 of them, in which case you're in line for less than full marks. And which 4 you choose is up to you. I just encourage you to implement them all. It's an assignment worth 15% of your final grade, but you got other constraints. That's your decision. The main point here is that you'll be uploading a single file, and I'll talk in a little bit about what format that file takes. If there's one overarching strategy I want to convey to you today, it's a strategy for developing and testing your code, which I've identified here on slide 13 with 3 points. I've taken these 3 points from the assignment question sheet itself. These same 3 points appear there, and they're when I say you're strongly encouraged, I think basically you have to follow this sort of format. You won't be tested if you did, but I can't imagine any other way of developing the code. And here it is. What I'll do for you now is just run through these points, the main concepts here, and then I want to illustrate these 3 points on the following slide. So the idea is for each function to start with a fresh script and write your code to implement a solution to the specification that appears in the assignment question sheet and test it. I've got something really interesting to say about testing in a moment. Test it that it works. When it does work, create a new file which defines the code in a Python function that has the same behavior. Test it again. And the third step, once your second step works, is to copy and paste your working function into your image processing.py file, and that's the one that's going to be uploaded. And here's the thing about testing. So I said you're going to be able to you'll ultimately upload one file to Blackboard, and it's called image processing.py, and it'll have as many as 13 functions inside it. We are going to be we actually have made available to students via Blackboard some test code. So what you'll be able to do is run your functions as defined in image processing.py. You'll be able to test them against our test code. And that test code is the code that the demonstrators are going to use when they assess your program, your submission in week 14. So that the intention of doing that is to take away anxiety and to take away uncertainty from you about, is my code correct? Rather than having you ask that question, or rather than having you need to ask that question, we're going to give you the tools to answer that question yourself. We're going to give you the test code that the demonstrators are going to use to assess your assignment. So you can check in advance if your code works correctly. So if you've got a solution that passes the tests, if you've got a collection of functions in image processing.py that passes all the tests in the test code that we've made available, you're a virtual dead certainty to get full marks in the assignment assessment in week 14. So we're not looking to trick students. We're not looking to create uncertainty. We're not looking to create anxiety. We're looking to give you as much feedback as you need to be able to do your own testing, so that you'll know as part of the test and development process whether your code is right. So here on this slide, I'm going to spell out with a tiny little example what I mean by the test and development strategy that I've identified here on page 13. So step 1 was each function's behavior to be written in its own script. So here's a really simple example. It's got nothing directly to do with the assignment, but it's the overall strategy I'm trying to convey for you. Suppose the function that you want to write is a function which takes the square of a number. So here's a simple program which does that. Here's our number, x equals 3. And then we can print the number squared. We print the number x and x squared. Remember, star in Python means exponentiation. So x star 2 is x squared. So there's a really simple program that takes a number, in this case 3, and prints the number x and its squared value to the screen. So then we can do our test and development in a file called square.py. Once our code works, What's step 2 says? It define code into a function in the same file, meaning the function appears in the same file. So step 2, what I mean is create yourself a new file, squarefunction.py, and this time we implement our function f of x as an explicit defined Python function. So these two scripts, separate scripts in steps 1 and 2, they both perform the same action. They both take an integer and print the integer and its squared value to the screen, to the console, I should say. The difference is that step 2 has the functionality implemented as a Python function. So line 6 needs to change a bit. This is the test code for implementing a square function as a function. And here, instead of the second argument to the format function being x squared, here the second argument is our Python function. And when that code is ready and tested and debugged, and you're happy that it's right, step 3 is really simple. You simply cut and paste the code, or copy and paste the code from your function definition and pop it into image processing.py that you're going to upload to Blackboard. And so that strategy is the one that I want you to follow when you're implementing each of the 5 and then 8 functions that are required in the Blackboard upload. And what that does, it allows us to really easily assess the code, because everyone's going to have the same file name, image processing.py, and we can automate the process of testing your functions against known solutions. And so that brings us to the conclusion of my presentation today, which is to talk about that testing and grading. So there are 15 marks total, 15% assignment. So you know when you're going about it, there's 2 marks for each of the correct implementation of the first 7 functions, and 1 mark for the correct implementation of unsharp mask. So 2 times 7 plus 1 is 15. And Python test script, which we published on Blackboard in the last hour or so, is going to allow you to judge the correctness of your implementations with easy to debug data. So I'm really happy with the way that we've structured that in terms of what it will do for you as students learning this material. Sometimes when you're with the assignment, you don't know what the answer is, or you don't know, is your answer correct? We're not going to tell you if your answer is correct. We're going to allow you to self-assess whether your answer is correct, which means that by the time you press submit and you upload your code to Python, to Blackboard, you'll have a very high degree of confidence in what grade you're going to get. So it takes a lot of that anxiety away. We're not about tricking you. We're about giving you the tools that you need to self-assess how good your implementations are. Okay, that's good. That's what I wanted to cover today with you today. I'd urge you to keep this lecture file handy. I've posted it in the questions lectures channel. I've also posted it in the week 10 course materials on Blackboard. I hope that you found today's presentation useful. And until we see each other on Monday, I'll say bye for now.